Okay, QZ is 17. KQ is 11. ZK is 6, so we need to be careful. That's 6 from intersection to intersection. That's why I call that. And BZ is 22. First of all, we need to make sure that these two triangles are similar because we don't solve for missing sides unless we know they're similar, because if they're not similar, then the sides aren't proportional. Well, they're obviously similar by angle, angle, squiggly. Very good. They're obviously similar by angle, angle, squiggly. We didn't have to do any work. That's already marked for us. So K, Q, Z. So that's K has no arcs, Q has 1 arc, and Z has 2 arcs. So it's 0, 1, 2. B, Z, J. All right. That part was definitely not difficult, as long as you can keep track of the order of the arcs. Okay, the next thing is that we are looking for JK. I recommend that you find JZ first, find JZ, and then we'll just subtract 6 from JZ. It's hard to say over and over. Subtract 6 from it, and then we'll know JK. LOL, JK. Huh. Okay, anyway, so let's find JZ. Okay. JZ is across from, you always look and see what it's across from. JZ is across from nothing. So what does it go with? It goes with the other one that's across from nothing. So I'm going to say 17 is to JZ as, now we just need to find 2 other things that go together. Let's see, 11 is across from double arc, and 22 is across from double arc. 11 is just half of 22. The scale factor is just 2. That's all there is to this problem, but people missed it on the quiz like crazy. So 17 is to JZ as 11 is to 22. I'll put my 2's look like my Z's. So, okay. So 17 times 22 divided by 11. Or you just know that you double 17 because the scale factor is 2. Okay, so JZ is 34, and then you simply subtract 6 from it. So I think JK was 28. Are we okay with that? The homework was super short. Here are the answers. I don't know, guys. Our kids got this worksheet, but apparently we don't have a digital copy of it. Show you what it looked like. It looked like this, but you're saying this wasn't online. So when you hear the word mean, you probably think average. You probably think add 2 numbers and divide by 2. Well, when you think mean, you're thinking of an arithmetic mean. But there are more means out there in this world. There's not just arithmetic means that you learn in algebra. There's also a geometric mean. So the arithmetic mean is when you add 2 numbers and divide by 2. What do we think a geometric mean is? Someone who doesn't already know the answer. So the arithmetic mean of 4 and 8 is 6. Let's step it up a notch. Step it up a notch. Instead of adding, how could we step up addition? Multiply. Good. So 4 times 8. Now wait, we already divided by 2, so can you step up dividing by 2? Ooh, square root. Yes, very good. So the geometric mean is actually the square root of the product. Instead of adding them and dividing by 2, we're going to multiply them and square root. So what's the geometric mean of 4 and 8? The square root of 4 times 8? 5.7. So in this case, because our numbers are so close together, so small and so close together, in this case, the geometric mean is actually really close to the arithmetic mean. Very good question. So Edriel asked, let's see. Okay, we're gonna skip that. I want to go over something first. Edriel asked, well, what if there's 3 numbers? Because in an arithmetic mean, if there's 3 numbers, you add them up and divide by 3. So in a geometric mean, if there's 3 numbers, which there never will be in this class, we're not going to go larger than 2 in this class, but yes, if there were 3 numbers in the real world, you would multiply them and cube root it. If there were 4 numbers, you would multiply them and fourth root it, so on and so forth. I was curious as to what geometric mean, like how people in the real world actually use it, because we all know how they use average. People average things arithmetically all the time. But why is there such thing as a geometric mean, and who would need to use it? So let me tell you why there is such thing. Lots of companies actually use geometric mean. Lots of investment bankers use geometric mean when different portfolios yield different amounts. So it's very important in money and banking, but that's not the example I'm going to give you. I'm going to give you an example of, you're going to buy a new camera, okay? You're going to buy a new camera, and the lens of the first camera is a really great lens. It's like a 200 zoom lens or whatever. But the ratings online, from 1 to 5, the ratings online, it got a 3 in the ratings. Now, this other camera only has 150 zoom, but the ratings online gave it a 5 out of 1 to 5. Now, I can't just add 200 plus 3 and divide by 2 to find the average of those two, because they're out of different things. They're on different scales. So geometric mean is used when two things are on different scales. So instead of adding them up and dividing by 2, that would give one of the ones way too much weight. That would give the lens too much weight. We don't want the lens to weigh that much, because we want the ratings to mean something too. So when things are on different scales, you can take the geometric mean and compare the geometric mean instead of, like, compare these two numbers instead of comparing the add up divide by 2 number. It works for, like, when companies get rated on, let's say they get rated on customer service, 1 out of 10, but then they get rated on environmental sustainability, and that's 1 out of 5. Well, those two numbers are on different scales. So anyways, that's enough of me rambling on. That's how people use it in the real world when they have different scales. Okay, let's look at what it's going to mean in geometry, because that's honestly all we care about, is what it means for us in geometry. It's going to be in the scope of triangles in geometry. Write this down, this definition, please. For any two positive numbers, A and B, the geometric mean of A and B is the positive number. That's important. The geometric mean is never negative, so you can throw the negative ones out. It's the positive number x such that A over x equals x over b. Just write it down. So take a look what happens. When we cross multiply, we've got A times B equals, what is x times x? Don't say 2x. X squared, yeah. And then when you're solving for x, you're trying to get it all alone. You're trying to do the opposite of what's being done to it. So what's the opposite of x squared? Square root. So isn't that exactly what I taught you? X, the geometric mean, is the square root of the product. That's what x is. When you solve that proportion, x is the square root of A times B. So that's what a geometric mean is. All right, let's find the geometric mean of 4 and 9. So step 1, you write a proportion. 4 is to x as x is to 9. Then you cross multiply. X squared equals 36. And then you take the square root. X is equal to the square root of 36, which is 6. I realize that when you solve for x, you get plus or minus 6. That's very important. But since geometric means are only positive, we would keep only the 6. Okay? Find the geometric mean of 10 and 40. Yes, I'll call on someone. Don't type the answer yet. You should be ready. Edriel, what do you get? Sorry guys, 20 is the answer. Very good. So you can do this, absolutely. This is the definition of geometric mean. But on a problem like this, if you were just to go straight to this and you know what that means, then that's fine with me as well. So the square root of 400. So you get 20. Either way, x is 20. If you want to set up the proportion every time, that's perfectly fine. And then you take the square root of both sides. So I want you to see it done both ways, okay? Now we're going to get into what this means for geometry, finally, after we practice a couple times. Okay, so take a look at this figure and just draw some conclusions, because this is the only figure that we're going to use geometric mean for. This is the only figure. So if a figure doesn't look exactly like this, don't use geometric mean on it. It's only going to work in this figure. You conclude that B is a right angle. So it's looking like we can only use geometric mean on right triangles, and that's correct. Ooh, similar by angle similarity. You're on to something. So we have to have a right triangle. What is this called? Wait. Quinn, what's that called? These right triangles are so special. Yes, they are. Why'd you put that in quotations? BD is an altitude. And it's not only an altitude, it's an altitude drawn to the hypotenuse, because AC is the hypotenuse. Alexandria, what is AB called? For the big triangle, what's the vocab word for AB? Yes, that's exactly what I wanted you to say. This is a leg. This is a leg, right? This is the hypotenuse, and this is the altitude. So all of those words are very important. And we're talking about the largest triangle only. We're talking about ABC only. We're not going to say, oh, well, BC is the leg of ABC, but it's the hypotenuse of BDC. No, we're going to call it the leg. We're not going to call it a hypotenuse, okay? So someone mentioned that those triangles are similar by angle similarity. And you're totally right. But there's not just two triangles similar. There are three similar triangles when you have a right triangle and you draw the altitude to the hypotenuse. So take a look at this figure right here, the purple one. We're going to take the little one out, and it's going to rotate, and they're going to drag it down right there. There we go. So there's one of our triangles. Then they're going to pull out the medium one, and it's going to be similar. And then they're going to pull out the largest triangle. There we go. Okay, so those are the three triangles. They're all right triangles, and they're all similar, like you said, by angle. So three similar triangles result when you draw the altitude, okay? Okay, now, for this part, just humor me and just listen to me, okay? I'm going to give you the real theorem, but then I'm going to try to say it in easier words to understand, okay? Ready? Theorem, here we go. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original and to each other. So they're similar to the original and to each other. Okay? So you have to, all of the words are important. Yes, it has to be an altitude. Yes, it has to be going to the hypotenuse. Yes, the triangle has to be right. And then it's similar to the original and each other. So three similar triangles. So in this picture, triangle ABC is similar to triangle ADB, which is similar to triangle BDC. Three similar triangles. I'll give you a minute to write down from this slide. All I want you to write down is the similarity statement, please. Okay, let's keep going. If triangles are similar, then their corresponding sides are, Ariana? If two triangles are similar, then their corresponding sides are proportional. That is one of the building blocks. That is the foundation to this whole unit. If two triangles or two polygons are similar, their angles are congruent, their sides are proportional. Angles congruent, sides proportional. All right, so if these two triangles really are similar, then let's set up a proportion so that we can solve for missing sides, okay? AD is to BD as BD is to... So what I did was I took the longest leg over the shortest leg, and I'm comparing that to the longest leg over the shortest leg. So hopefully you realize, oh, it doesn't appear. DC. So that's like long leg over short leg equals the long leg of the other triangle over the short leg. And when we write that proportion, something should be screaming at you. Look at that. AD over BD equals BD over DC. We use BD twice. This should look like, to you, it should look like a geometric mean. If I named this 8 and I named this 13 and this is 2, then this proportion would say 13 is to x as x is to 2. And that is a geometric mean right there. Okay. So once again, you're not going to write it. You're just going to listen and you're going to absorb. Are you absorbing? Okay. So if those triangles are similar, then we have a geometric mean proportion. The altitude is the geometric mean of the two segments of the hypotenuse, and that's a theorem, okay? The altitude is a geometric mean between segment A and segment B. Always, every time you have an altitude drawn of the right triangle to the hypotenuse, okay? So every time, no matter what A and what B are, A is to X as X is to B. This is one of our, what geometric mean is all about is it's a shortcut, okay? It's going to help us solve for sides of triangles without having to say, oh, these two triangles are similar. Oh, okay, now I can set up a proportion. We're going to know the proportion right away. So A is to X as X is to B. You use the two segments of the hypotenuse. So an easy way to remember that is to remember this proportion right here. Segment is to altitude as altitude is to the other segment. I couldn't call it seg again because I'd be afraid you'd use the same number twice and that would get you into a mess. Okay, so the segment of the hypotenuse over the altitude equals the altitude over the other segment of the hypotenuse. Okay, try it. I probably made it a lot more complicated than it is, but I wanted to give you all the information. You're going to do these and you're going to be like, this is so easy. And I'm going to be like, you're right. Try this one. These proportions, like that proportion that I just told you, we at Cy Falls just kind of made that up. You can make up your own proportion. That proportion, you're not going to see that in 15 textbooks across the country. They're all going to have their own little shortcut proportion. So whatever proportion makes sense to you, if you want to do seg 1 over altitude equals altitude over seg 2, then totally do that. Or maybe you could put them as like underscores so that it doesn't look like times 1 times 2, whatever. All right, so to solve this problem, we would do segment of the hypotenuse over the altitude equals the altitude over the other segment of the hypotenuse. 2 is to X as X is to 8. That's the same as saying that X is the geometric mean of 2 and 8. So honestly, guys, if you get this problem in front of you, if you're given this problem and you just go to your calculator and do that, I would be totally okay with that. That would be totally fine with me because you see the connection that the altitude is the geometric mean of the segments. So if you go straight to your calculator and you do the square root of 2 times 8, then that's fine by me. But set it up and show the work if you feel like you need to, if you feel like you're going to make a mistake or mess up if you don't do the proportion, okay? Very good. The answer is 4. Square root of 16, x is 4. So the altitude of that hypotenuse is 4 units long. Okay, last theorem of the day, I promise, okay? Next one, we have one more shortcut, one more proportion that's going to help us solve for sides. So it separates the hypotenuse so that the length of each leg, I'm going to put an X by one of the legs, is the geometric mean of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. So there's where the adjacent segment is. I know this is so wordy. I get it. I'm on your side. I know this is confusing. So what that is saying is that, there we go. X, here's our leg. X is the geometric mean between the hypotenuse, which I just called A, and the segment of the hypotenuse that's closest to X, B. A is to X as X is to B. The leg is the geometric mean of the hypotenuse and of the adjacent segment of the hypotenuse. A is to X as X is to B. It'll make more sense the more you do of these. That says the same thing. Okay, so here's proportion number 2. There's only 2 proportions, so don't worry about that. But you do need to memorize them. There's only 2. Test is Friday. Memorize them before Friday. All right, so the hypotenuse over the leg equals the leg over the adjacent segment of the hypotenuse. Okay, let's try one. I'll write it down. Put the hypotenuse over the leg, and then put the leg over the adjacent segment. So you need 2 things for this problem. You need the hypotenuse, and then you need the segment closest to X. Those are your A and your B. You need the hypotenuse, you need the segment closest to X. Okay, it's a dash to type the right answer. Who's going to get it first? Type it. Go. Oh, 12. 5. Do we disagree here? 12. I'm getting more 12s than 5. Sorry, Rishi. Let's go over it. Okay, first thing that it says is to put the hypotenuse. The hypotenuse of this triangle is 18. And then X is the geometric mean, so you always write the mean twice. And then this one says adjacent segment. Which segment is closer to X? Which is adjacent to X? And in this case, it's 8. There's a huge lag time between when I write something and when it shows up on y'all's screen. Okay, so X squared equals 18 times 8. Square root both sides. X is 12. It's not plus or minus 12 because sides of triangles have to be positive. Okay? X is 12. Like I said, if you can look at this and if you know geometric mean well enough, then you could just look at this and literally do, that's the geometric mean, that's the square root of the product, 18 times 8. Okay, same thing. This time you have to draw the triangle yourself. Take a whack at it. Hopefully you have a picture by now. Let's make sure we all have the same picture. I'm going to draw the triangle kind of like all the examples have been, although you don't have to. I'm going to put the right angle here, although you could have put the right angle somewhere else. The altitude to the hypotenuse, okay, there we go. The altitude to the hypotenuse of a right triangle divides the hypotenuse into segments 3 centimeters and 27 centimeters long. Find the length of the altitude. Remember, there's one proportion when you're looking for altitude. There's another proportion when you're looking for legs. So make sure you have both of those proportions written down. One for altitude, one for leg. This one we're looking for the altitude. So the proportion is seg 1 over altitude equals altitude over seg 2. 3 is to x as x is to 27. Or you just look at it and you take the square root of 3 times 27, which is the geometric mean of 3 and 27. That can be flip-flopped. Yes, your 3 times 27 is the same as 27 times 3. Yeah, so don't worry about that. So the biggest part of this lesson is having to memorize those 2 proportions, or just figure out in your brain how geometric mean works, whether you're memorizing the proportions or not. Okay, final answer? 9. Yes, 9 is the final answer. Beautiful. Last problem of the day. find the values of the variables, and you're going to have to round on some of these, maybe all of them. And when you do round, round to the nearest tenth. I'll call on 3 people after I give you a minute to work this. I would recommend you start with y. I'll start working these. When you have the answer, you can type it in. I would do y first, because to me that one's the easiest. You just use the 2 segments. 7 is to y as y is to 9. You're going to set up 3 different proportions, and you're never going to use one of your answers in a different proportion. Never use what you got for y to help you find x or anything like that, okay? The proportion for x would be, let's see, you need the whole hypotenuse for this one. So the proportion for x would be 16 is to x as x is to the adjacent segment, 7. And then for z, it would be 16 is to z as z is to the adjacent one to z, 9. So it's set up 3 totally different proportions and treat each variable separately. Dustin's getting 42. Oh, okay, there you go. 10 point, nearest tenth would be, there you go, 10.6. What else do we have, guys? 7.9. And Lars, you got a whole number? Rishi, of course you can do Pythagorean theorem, but that would mean you're using one of your answers. That puts you in double jeopardy. If you got y wrong and you do Pythagorean theorem with y, then you're going to get y wrong and you're going to get z wrong. Or you're going to get y wrong and you're going to get x wrong. So I don't ever use my answers to find something else unless I have to. Plus, if you round y and then you do Pythagorean theorem, your x is going to be further off. You would have to use the exact value of y, and we haven't talked about how to work with radicals yet. One more thing about geometric mean that we're not really going to use in this class, but it's the geometrical application of it, so I just want you to know. The geometric mean of, let's say the rectangle, let's use one we've already used today. Let's say this is 10 by 40. What is the geometric mean of 10 and 40? We did it earlier today. So the geometric mean between those two numbers is the side length of a square whose area would be the same area as that rectangle. That's what a geometric mean is. That's how we use it in geometry. Does that make sense? Okay, so the geometric mean of 10 and 40 is 20. 20 is the side length of the square that has the same area as the rectangle. What's 20 squared? The area of that is 400. What's 40 times 10? The area of that is 400. Does that make sense? So the geometric mean between two numbers is the side length of a square that has the same area as the area of the rectangle that would be made by those two numbers. I don't know, I thought it was cool. Okay, go do your homework.